Welcome. In this session, we will learn one more class of discrete time system that's referred as stable or unstable discrete time system. Now, in the previous class, we learned the constraint of linearity. That is, if the system is linear and time invariant, it defines a new class of discrete time systems where the input and the output is related by convolution sum, where the input and output is related by convolution sum or simply convolution formula. So we say the input output relation of an LTI system is related by this convolution, means the output is the convolution of input and the impulse response of the system. Now in this session we will involve one more additional constraint of stability and see how do we define first a stable system, general discrete time stable system. Then we shall see if the system is linear and time invariant, means if the system is LTI, if the system is LTI system, what is the condition of stability for this LTI system? So what is the condition of stability of this LTI system? That we shall learn in this session. All right. So first, let's see what's a stable system. So what is a stable discrete time system? So this is our first topic. Now there are several definitions in the literature in electrical domain that we can use to define what's a stable system. For example, if we from network theory, in network theory, we say if the natural response or the transient response, if the natural or transient response of the network goes to zero, means if the transient or natural response dies as t approaches to infinity, then we say that network is a stable network. So this is used in network theory. This definition of stability is used in network theory. For example, if we say we have an RC network, and if we apply an input to this RC network, and we say output is VCT across this capacitor. So this is our R, this is our C. So the voltage across the capacitor is the output of this network. Now we know from network theory or differential calculus course that there are two parts of this VCT. One is referred as transient part or the natural response part. Another is referred as steady state part or the forced response part, are simply the complementary functioning natural response. So there are two parts of this VCT. One is referred as, means the output voltage has two parts. One is referred as the natural response part, another is referred as the this particular integral. In maths we call it per Q integral. In network theory we call it steady state response, or control theory we call it steady state response or forced response. So if VCT, remember the definition of this stability for network theory, if VCT goes to zero as t approaches to infinity, we say this RC network is a stable network. This is the definition used in network theory. Same way, there are several definitions used in control theory. For example, the popular definitions are, in control theory we have several definitions. For example, we have the pole zero location. What is the location of poles and zeros? If the poles and zeros of the closed loop transfer function lie on the left half plane of this, if the poles and zeros, means if the pole zero lie on the left half plane of the complex plane, it is sigma This is J omega. If all the poles are located in this side, then we say that system or the control system is a stable system. Same way, there are other definitions in control theory. One is RH, one is Routh-Harvey's criterion, Nyquist plot, and so on. So there are several definitions of this stability to check whether a system is stable or not, used in control theory. Now the definition that we are going to use here to define whether a system is a stable system or not is referred as bounded input, bounded output stable system. Means if bounded input, bounded output stable system. So the definition we'll use is referred as bounded input, bounded output definition. This is called as BBOO. What do we mean by bounded input? Means if the input is finite, and if the resultant output of the system is also finite for this finite input, then that system is referred as bounded input, bounded output stable system. What do we mean by this? Means if the input to the system is finite, and if the resultant output of this system, let's call that y of n, is also finite for this finite input, then we say this system is bounded input, bounded output stable system. So this is the definition used in this, that we'll use in this discrete time system course. So this is the definition that we'll follow. So if the input is finite, and if the resultant output for this finite input is also finite, then we say that system is bounded input, bounded output stable system. Now mathematically, we can define this criteria like this. So mathematically we say if x of n is the input of the system, we say this is the input of our system. Now we say this is finite, means the maximum value of this is finite. We say the magnitude of this x of n is finite, and let's suppose the maximum value of this x of n is m of x. And we say, how do we say this is finite? Mathematically we write it like this, means this is less than infinity. That's how we write this. M of x is a finite quantity. We say the maximum value of x of n is m of x, which is a finite quantity. We write it like this. Then the output for this system, then if the output for this system whose input is x of n, if the maximum value of this output is, let's call it m of 1 y. So if the maximum value of this output is m of y, and this is also finite, how do we write finite again? We use this. So if the m of y is also finite quantity, then this system is a bounded input, bounded output stable system. So this is a BBOO stable system. This is the definition used to check whether the system is finite or not. Now let me give an example to illustrate that this, how to check whether the system is bounded input or bounded output stable system. Let's suppose our x of n is the input to a system whose output is y of n, and y of n is x of n. So let's check whether this system is a stable system or not. So this is the input-output relationship. Now let's see whether this system is a bounded input, bounded output stable system. Now first of all, if we say input is bounded, means the maximum value of input, let's call it m of x, and we say this is less than infinity. So the maximum value of m of x, x of n is m of x. Now remember, e here is the same. The value of e is the same, 2.71 something. 2.71 something. I don't remember it exactly. It's the same value, right? So we say the maximum value of x of n is m of x, and we are saying that this is a finite quantity. We write it like this. Now the max, to check if the output is bounded or not, take mod on both sides. So if we take mod on both sides, this is what we get. So this is the input output relationship is this. Take the mod of the magnitude of this output. The so we'll have mod of e raised power x of n, and you can see this is same as mod of x of n. This will be same like this. Now we already defined it like this, means the magnitude of maximum value of x of n is so m of x. So the maximum value of m of x, this x of n is m of x. Now you can see the maximum value of y of n corresponding maximum value of y of n e to the power of m of x. Now if m of x is a finite quantity, means if this is a finite quantity, for example 2, 5, 10, anyway of these, so m of x is a finite quantity and this value is a finite quantity, means if this is less than infinity, you can see this e to the power of that quantity is also finite. So e to the power of that value is also finite. This may be a larger value, but you can say this will be still a finite quantity, means magnitude of y of n will still be, even if x of n is this maximum value and we know that is finite, then y of n, corresponding y of n will still be a finite quantity, and you can see this will be less than. Now from this you can write the value of, means the value of y of n varies from this x of n to the power of minus x of n, and if we substitute, this means the maximum value of this varies from this to this, means the lowest value will be this, maximum value will be this. Okay, so this you can write as m of x y of n e to the power of m of x. So this is the minimum value of y of n, this is the maximum value of n. I'm expanding this mod here. Please understand this. I'm just expanding this mod here of y of n. So this is the value of y of n if the maximum value of x of n is m of x. This is where the value of y of n vary between. So in other words, if x of n is a finite quantity, y of n is a finite quantity. So in other words, this means this system is a Bible stable system. So this is a Bible stable system. All right. So this is how we check whether the system, discrete time system, is a stable system or not. Now let's suppose our system is LTI system. Now let's see the criteria for an LTI system. Now if the input to this LTI system is x of n, whose impulse response is h of n, then the output is y of n. Now we know output is related to input by this convolution operation between x of n and impulse response of the system, and we know that we can write this convolution like this. This is minus infinity to infinity x of n minus k h of k, and you can also write it like this. We have derived this one, but you can prove that this is same as x of k h of, this is same as this h of n minus k. So this is referred as the commutative property. This property is referred as commutative property. We will see once we see the we shall learn this in the properties of convolution. That will be next lecture hopefully. So this is the input output relationship in an LTI system whose impulse response is h of n. Now we say input to derive the condition of this stability for this LTI system. We say the maximum value of x of n is m of x, and we say this is a finite quantity. This is how we write that this is a finite quantity. This is the meaning that x of n is a finite quantity. Mathematically, we write it like this. We say maximum value of x of a is m of x, and this is a finite quantity. Now, to determine whether the output is stable, means finite or not, let's check that. So taking mod on both sides, let's consider this one. So taking mod on this, to output, this will be same as mod on the left hand side, h of k. So this is equal to this. Now I'm going to use a property that mod of a plus b is less or equal to mod a plus mod b. Magnitude of a plus b is less or equal to magnitude of a plus magnitude of b. All right, so using this property, I can write this sum. There are actually infinite terms in this, and this is same way applicable to infinite terms. If you have now 3 terms, you can say this is mod A plus mod B plus mod C. So you can write this. So even if you are infinite terms, you can write it like this. So you can say this is minus infinity to infinity, magnitude of x of n minus k, h of k, magnitude. All right, so this is equal to this. Now you can say this is same as k running from minus infinity to infinity. Now we know mod of AB is equal to mod A mod B. So we can write it. So there are 2 terms here. We can write the mod separately. Now, next question is, when will be this y of n maximum? When will be this magnitude of this y of n maximum? If we substitute, from this we can say if we substitute the maximum value of x of n, and we know from this the maximum value of x of n is m of x. So the maximum value of x of n is m of x. Now, what is x of n minus k? X of n minus k is simply the shifted version of x of n. It's simply a shifted version of x of n. So the maximum value won't change. So substituting this to get the maximum value of y of n, let's substitute it. So this will be simply m of x, h of k. So this will be summation k running from minus infinity to m of x, where m of x is the maximum value. So our aim is to get the maximum value of y of n. So you can see m of x is independent of this summation. So you can write it m of x summation k running from minus infinity to infinity mod of h of k. So this is equal to this. So mod of this is equal to this. Now you can see when will be this y of n finite. From this y of n is the maximum value of this y of n will be finite. We know m of x is finite because we already assumed that this is a finite quantity. Now this is a finite quantity. We know maximum value of y of n is product of m of x with this quantity. Now if this quantity is finite, then y of n means the maximum value of y of n is finite. So you can say this is finite if this quantity is finite. Means if this quantity is finite. How do we write that this quantity is finite? In other words, if k running from minus infinity to infinity, h of k is less than infinity, and we know product of 2 finite quantities is a finite quantity. So if this is true, means if the summation of h of k, where k running from minus infinity to plus infinity, is a finite quantity, then the system, means the LTI system, is a stable system. In other words, y of n will be a finite quantity. If the input was finite, the output is then finite if this quantity is finite. Now, what's the meaning of this quantity? This simply means if the impulse response of the system, means if the impulse response of the system is absolutely summable. This is the meaning of this term. If the impulse response of the this LTI system is absolutely summable. What is the meaning of absolutely summable? Means if you sum all the values of the impulse response of this system, if that turns out to be a finite quantity, then this system is a stable system. So this is the criteria or the condition for a system, for an LTI system to be a stable system. So this is the condition for an LTI system to be a stable system. This is the condition for an LTI system to be a stable system, and the condition is that the impulse response of the system should be absolutely summable, and you should be able to sum the impulse response of the system. Now same way you can write this condition for a continuous time system. If the system was continuous time, then if this quantity is finite quantity, then we say this continuous time LTI system is the stable. So if the impulse response of the continuous time is absolutely integrable, in continuous time the condition is if the impulse response of this continuous LTI system is absolutely integrable, then that continuous time LTI system is a stable system. That LTI system is a stable system. Let's solve some examples so that we may get a better feel of what we mean by stability. Let's suppose the impulse response of the system is a raised power n u of n. Let's check whether this system is a stable system or not. Let's confirm this whether this system is a stable system or not. So what's the criteria? This is the criteria. If the impulse response is absolutely summable, then that. So let's use this condition. So this will be k running from minus infinity to infinity, h of k sum. Let's call this sum as s. Let's call it simply s. So s is equal to this. So substituting the value of this h of k is simply a raised power k, replacing k by n. You can also use this n instead of this k. So there is no need to change the variables here. You can directly use that. Now, using the definition of u of k, we know u of k is equal to 1 when k is greater or equal to 0, and it's equal to 0 when k is less than 0. So what will happen to this sum? This sum is simply summation k running from 0 to infinity, a raised power k, and magnitude of this. Now from this sum you can see this becomes a GP series, and this GP series is running from 1 to infinity. You can say this is a raised power 0, a raised power 1 plus a raised power 2, sorry, not a raised power 2, a square, and actually there is mod, so there is mod a cube and so on. Now you can write it like this: 1 plus mod a square plus mod a cube plus so on. So this is a GP where the common ratio here means the R is equal to mod a. Now you can say this is our sum. So the sum of this impulse response is equal to this, and we know that this GP is equal to 1 by 1 minus R, where R is mod A. So you can say this is equal to C if the common ratio or the magnitude of this A is less than 1. So we say this S is a finite quantity, meaning the sum which is defined as k running from minus infinity to infinity, magnitude of h of k is equal to 1 by 1 minus a. We say this is less than infinity if magnitude of a is 1. So this is the condition for the system. Means if the mod a is less than 1, this is the condition for the system to be stable system. Now let's suppose a is equal to 1 by 2. Let me give a practical example. So a is 2. So what's the impulse response of the system? Impulse response will simply be 1 by 2 raised to n u of n. So what will be the sum required from this formula? This will be simply 1 by 1 minus 1 by 2 now, and if you evaluate this will be simply 2. So this sum is a finite quantity. You can check this is a finite quantity. So this system is this impulse response is integrable. So this impulse, sorry, summable. So this sum is summable. So you can say this system is a stable LTI system. So this is about stable LTI system. So the definition that we follow is to check whether the system is bounded input, bounded output, stable system. And stability, this stability criterion defined as a new class of systems, and this is very, very important when we design a discrete time system. All right, so let me stop here. In the next session, we'll learn about causal systems.